Well, hello and welcome again to Maths 315, and we've been looking at the sums series and summability, and this is the fourth recording for chapter 3. We finished up last time with this very lovely ratio test, which is a test used when you've got exponentials and factorials. And just to remind you of this again, you look at the ratio. If you've got your sigma an, you looked at the ratio of an plus 1 over an. You take a limit. If that limit exists and equals r, then the series converges if r is less than 1 and diverges if r is bigger than 1. And if r happens to equal 1, well, bad luck, the test doesn't tell you anything. And I did last time the very first example here, and I want to do the next two examples here. So here is the solution to the second example. So we're looking here at sigma 2 to the n on n factorial. Now in this case our sequence, the an's, are 2 to the n on n factorial. And we're going to look at, so r then is the limit of the ratio an plus 1 on an. So that means I replace n with n plus 1 divided by n plus 1 factorial. Now we're going to divide by this. And so when you're dividing two fractions, you invert and multiply. So I'm going to multiply by, turn this upside down, just to save a bit of time. So I'm taking this one, divided by that, we invert and multiply. Now we saw before that the n factorial on n plus 1 factorial collapses down to n plus 1. And we've got 2 to the n plus 1 divided by 2 to the n, well that's just 2. And this limit is easy to work out. Again, this turns out to be 0. So the limit exists, and the limit, this is my r value, and r is less than 1. So the series converges by the ratio test. Series converges by the ratio test. Now the third example is slightly more difficult, but you'll see this is quite a nice example, and you'll see something like this one in the assignment. So this is probably a good one to particularly take note of. This is sigma n to the n on n factorial. And in the assignment I'm going to get you to look at it the other way round. So this is probably a useful tool for helping you with the assignment question. So here we've got a sub n as n to the n on n factorial. Now again, we're going to look at the ratio an plus 1 over an, and we're going to look at the limit, and I'm going to call that number r. So we plug it in. Where you see n here, you copy n plus 1. So you've got n plus 1 to the power n plus 1 over n plus 1 factorial. And again, I'm going to invert and multiply. So I'm going to multiply by n factorial over n to the n. Now we've seen before that n factorial on n plus 1 factorial is just n plus 1. So I copy everything else down. And I can cancel one of these off with one of these up here. So I'm going to get n plus 1 to the n over n to the n. And these are both to the power n, so I can pull them all together under one big bracket here and write this as n plus 1 over n all to the n. And finally, I'm going to divide the n into these, so I'm going to get 1 plus 1 over n to the n. And we've seen this limit earlier in the course. You may have seen it before then as well. If you take a limit as n goes to infinity of this quantity here, we proved before this leads to the number e, to about 2.71828. Now this number, this is the ratio here, and the ratio now is bigger than 1. So that tells me this series diverges by the ratio test. If the value of r is bigger than 1, then the series diverges. That's a nice example, and I said you'll see something similar in the assignment. Well, finally, in this section, we're going to have a look at what are called alternating series, and these are very, very strange objects indeed, and we're not going to delve too deeply into these because these are also quite mysterious and quite horrifying, in fact. as we'll see at the very end. So up to this point, we've been considering values of series whose terms are positive or at least non-negative. Some of them might have been 0, but they're at least positive or non-negative. I'm now going to consider series where the sign of the terms alternates between positive and negative. And I'm going to define what we call an alternating series. So if we take a sequence of terms that are all positive for every n, and I'm going to change every second sign, and the way we do that is we put a -1 to the n or a -1 to the n plus 1 there. And this is called an alternating series. So for example, if we take this series, I'm going to replace n with n plus 1 here so that we start off with something positive. So n equals 1. So we get -1 squared is 1, and I get a 1, and then I'm going to get a -1 over 2, and a +1 over 3, and a -1 over 4. So every second sign it alternates. Or rather, the signs alternate as we move through, plus, minus, and so on. And that's the alternating harmonic series. Now we've seen that if we put plus signs everywhere in here, we know there's diverges, but what happens if we put minuses every second term here? Well, that's an interesting question. Does it converge? Does it still diverge? Does it converge? And in fact, what does it converge to? Well, that's a more difficult question. I'll tell you the answer to that, but we won't derive that here. We've got a nice test to deal with series such as these, and it goes back to the mathematician Leibniz, who was around about the same time as Isaac Newton. Leibniz was the fellow who co-discovered the calculus. About the same time as Newton. Leibniz was in Germany, Newton was in England. They didn't communicate. There was no phones in those days, and certainly no emails, so they worked on this separately, and about the same time they seem to have come up with developing the calculus, but Newton was probably got there first, but there's still debate about that. Anyway, this test goes back to Leibniz and is sometimes referred to as Leibniz test, which is what I'm going to call it, in fact. Other people call it just the alternating series test or Leibniz's test. It's easier to write Leibniz, I think. So here are the ingredients. As with most theorems, conditions apply. So what are the conditions here? Well, we've got an alternating series. This can be n or n plus 1, doesn't matter. And the first condition is that an plus 1 is less than an. That is, the terms have to be decreasing, strictly decreasing. Each term's got to be getting smaller and smaller as we move along. And secondly, the limit, and I should have written in here as n goes to infinity, of course. The limit as n goes to infinity of an is 0. So this simply says that the terms are decreasing and the general term goes to 0. Now Leibniz's test says if that happens, then this infinite series converges. Now don't confuse this with other series tests. This only works for alternating series. Just because the general term goes to 0 generally does not tell you whether the series converges or not. But for an alternating series, if the terms are decreasing and all you need is that the general term goes to 0, then the alternating series converges. Now the proof of this, well, I'll go through it here. You won't be expected to reproduce the proof, but I'll just go through it quickly here and you can have a read of it later here. So we let Sn be the partial sums for this one, and I'm going to take the partial sums of an even number of terms. So I get a1 minus a2, a3 minus a4 up to a2k minus 1 minus a sub 2k. Now, since the terms of the series are decreasing by assumption, that means this number is less than that number, this number's less than that one, this number's less than that one. The sum of that means all of these brackets are all positive, and that means the partial sums are all positive. And that means this sequence then is an increasing sequence. an increasing sequence. On the other hand, going back to this sum here, I'm going to re-bracket things a bit. I'm going to move the brackets across to these. So I'm going to write this as A1 minus A2 minus A3. So just take these brackets out, you'll see you get back to here again. So I've got A1 minus something, and then I can say minus A4 minus A5, minus A4 minus A5, and I'm going to get minuses in front of every bracket, and I'll get a minus A sub k at the end. So these are all negatives, and what's in the brackets are all positive. So I get A1 minus something, and that's going to be less or equal to A1. In fact, strictly less than A1. That means these partial sums are bounded by the very first term, and they're decreasing. So they're bounded, they're all less than that. That means that this is a monotonic increasing sequence, because we set up here that S sub k is an increasing sequence. So it's a bounded monotonic increasing sequence. So again, by the monotone convergence theorem, we've used that so many times, this converges. Now this deals with what happens for the even terms. Now for the odd terms, well, suppose the limit that we find for the general term is L, then I can write the sum of the partial sum for the odd terms is the partial sum for the even terms plus this last term. And if we now take limits, then we've seen that this sequence converges, we've supposed that converges to L, and that says the limit as n goes to infinity of the partial sums of the odd terms is the limit of this one, which is L, plus this limit, which is 0, that was by one of our assumptions, and that's L. And that means the partial sums of the odd number of terms also goes to L. So in either case, Sn goes to L. Goes to L for the evens, and it goes to L for the odds. And that's a little proof of that one. Now, example of we're going to now show that this alternating harmonic series in fact converges. Now that's the surprise. In other words, if we take 1 minus a half plus a third minus a quarter plus a fifth, and we keep doing this forever, then this in fact will converge. Now in fact it happens to converge to log 2. That's another surprise. It converges to log 2. Now I'm not going to prove this here, but this is another amazing fact that if you add up this infinite series, it gets closer and closer to log 2. Here's a little proof of this. This is how we would set this out. So here's our alternating harmonic series, and I can think of it as minus 1 to the n plus 1 times an. Now the an then is going to be just 1 over n. Now clearly this is a decreasing sequence, right? A 1, a half, a third, a quarter, the terms are getting smaller, so it's decreasing. The limit of this is easy, that one is just 0, and that's it. We've checked the two conditions. So by Leibniz test, this alternating harmonic series, better put in the n equals 1 there, this converges by Leibniz's test. So the alternating harmonic series converges by Leibniz's test. Now, second example, we're going to look at this one here. This is minus 1 to the n. This time it's 2n minus 1 on n squared plus 3. Now, in this case, the an, the bit that's not alternating, is 2n minus 1 on n squared plus 3. Now, you've got to be, I'm not going to be too fussy here with the decreasing business, but I just wrote out the first few terms of this. So I put n as 1n, n as 2, 3, 4, and so on. Now, unfortunately, this one actually is, this one here is actually So A1 is actually less than A2. In other words, it's not decreasing the first two terms. The second term is bigger than the first term, not less than it. Well, that's unfortunate. However, if you put these over a common denominator, then you get 36 on 7 12 84, and then you get 35. So in fact, A2 is bigger than A3. That one's bigger than that one. And then this one is bigger than that one, and so on. So I'm going to say, even though it doesn't work for the first two terms, the AN is eventually decreasing. Now in practice, when you're doing these, don't worry too much. You'll always have ones that are decreasing. But you need to just note it. You don't need to do much more than just say that AN is eventually decreasing. You can prove this, but it takes a lot of fiddling around, but I'm not going to worry too much about that. You then check that the limit of this general term is 0. Well, that's fairly easy to see there. The money on the top, you've got a 2n on the top and n squared on the bottom. And so the bottom's going to dominate, and you'll get a limit of 0. You probably should put in a little bit of working out there to show that this is 0. And then that means this infinite series, I better put the n equals 1 in there. This infinite series then converges by Leibniz's test. And that's how we show this here. Converges by Leibniz's test. Don't confuse this with the other tests. This only works for alternating series. Now, the next little bit is not examinable, and if you've had enough, you can leave this bit. But for those who are interested, I wanted to show you just a little bit, rather some surprising facts. And this is to do with absolute and conditional convergence, but this is not examinable, but it may be, I hope, is some interest to you. Since the alternating series is less than the non-alternating series, it follows immediately from the comparison test that if this one here converges, then so does this one, because it's less than it. That is, if the non-alternating series sigma AN converges, then so does the corresponding alternating series minus 1 to the NA sub n. An alternating series that, for which the corresponding non-alternating series converges, is said to converge absolutely. This one is said to converge absolutely if the corresponding non-alternating series converges. A convergent alternating series for which AN diverges is called a conditionally convergent series. And I'll show you in a second what I mean by using this word convergent. Conditionally convergent. Now, as a simple example of that, if we take Euler's series, there's Euler's series, and we know that this converges for n equals 1 to infinity. This converges, and if I look at the alternating version of this one, making every second term negative, then this one is absolutely convergent, because if you take away the wobbly terms here, then the series you get converges, so that's absolutely convergent. On the other hand, this one, the alternating harmonic series, is conditionally convergent, because if you take away the minus 1 to the n plus 1, then you get the harmonic series, and we know that that doesn't converge. So this one is an example of a conditionally convergent series. Now, these conditionally convergent series are really crazy, and they caused mathematicians a lot of grief until analysis came along, in fact, to try and sort these things out. The reason they caused grief, I'm going to show you why they caused mathematicians grief, because series that do not converge absolutely have the very bizarre property that the terms can be rearranged to obtain a different sum from the original one. Now think about that. If I give you 5 numbers, you can add them up in any order you like, And if you don't make a mistake, you'll get the same answer every time. For these conditionally convergent infinite series, if you change the order in which you add up the terms, you can actually change the sum. And I'm going to show you a little example of a rearrangement here. So here's our alternating harmonic series, 1 minus a half plus a third minus a quarter plus and so on. And we know that this converges to log 2. We haven't proven that, but I've told you that's what it does. So that means log 2 is equal to 1 minus 2 plus a third, minus a half plus a third minus a quarter plus a fifth and so on. Now I'm going to reorganize, I'm going to change the order in here. I'm going to reorder this. And what I'm going to do is I'm going to take 1 minus a half minus a quarter, and then I'm going to move the third after that. So then there's the plus a third. Then I'm going to take the next two terms that have got negatives. These have got for even numbers. So I'll take minus a sixth and minus an eighth. And then I'm going to add in the next odd numbered term, 1/5. Then I'm going to take the next two even ones, so minus a tenth minus a twelfth, and add in the next odd one, 1 in 7. And I'm going to keep doing this through the whole of the infinite series. I'm changing the order in which I add them up. Now I'm going to put some brackets in. So I'm going to bracket those two terms together, leave that alone. Bracket these two terms, leave that one alone. Bracket these two terms, leave that one alone, and so on all the way through. Now comes the scary part, because work out what's going on inside the brackets. So 1 minus a half is a half, and then I copy minus a quarter. Now a third minus a sixth is a sixth. Minus an eighth, copy. 1/5 minus a tenth is a tenth. Copy minus a twelfth, and you keep going. But I can these are all even now. Isn't that a surprise? I can factor a half out, and I then get 1 minus a half plus a third minus a quarter plus a fifth. But that's what I started with. So I've now shown that this log 2 that I started with is equal to a half of log 2. This is crazy, but it's correct. There's nothing, well, log 2 equals a half log 2 is not a correct statement, but you can make these infinite series add up to anything you like by rearranging them. This caused mathematicians a lot of grief, but unfortunately this is just what happens naturally for these conditionally convergent series. It doesn't happen for the absolutely convergent series, only the conditionally convergent series. So here, changing the order of the summation changes the sum. And in fact, the story is even more horrendous, because in fact a conditionally convergent series can be made to have any sum we want. I can make this harmonic series add up to 103 by just reorganizing the order. Right. A little typo there. And so we can even make it diverge by a change of order. I can even make this convergent series, I can make it diverge by changing the order. So hence, when we say that an alternating series converges, what we mean is that it converges provided we take the natural order of terms and we don't rearrange anything. Because rearranging conditionally convergent series can change the sum. And that's the end of chapter 3.